Okay, here we go. Let's have a look.
I'm sorry, bro. I was fine. Yeah, because I see you've been watching Crosstat Fitness. Crosstat Fitness and watching.
Okay, how about this? Let's just go. I'll just go through the test. Do you think there's some questions that arose? Okay, so two horizontal forces, 120 newtons to the right, 170 newtons to the left, are exerted on a crate. What's the net horizontal force? 50. 50. To the left, to the left.
Don't.
50 newtons to the left.
I got that one right.
Yeah. That was the only one I got right. I'm gonna be honest with you.
Okay, what about this?
The first try.
So now let's talk about this one. So a cable pulls a crate to the right, but the crate remains motionless.
So is it one
Okay,
of the
so let's
ones?
raise your hand if you want to. We got too many people talking. Right there, yes.
I know the answer. Does that count?
Okay, but I want you to tell me why. What's going on?
So if it's pulling to the right but it's not moving, then the friction is the same side as the same.
They're balanced out.
Okay, good. Yeah, these are balanced forces. The net force is 0, isn't it?
Yeah,
Right.
that's what I meant.
Okay, so that means that the pulling force and the friction force must be equal in magnitude and opposite in direction. Okay, so if we're going to draw a free body diagram correctly, the vectors start at the dot, right? And they're gonna point in the directions that the forces pull. So if the cable is pulling to the right, then that's going to be the tension force to the right. So it's probably this guy, isn't it?
Yeah.
Right? Tension force to the right is equal to the frictional force that's resisting it. Yes, sir.
Is there ever a situation where the arrow wouldn't be originating from the dot?
Never. Never. Not with the free body diagram.
There's other diagrams though, right? What are
Well, yeah, but we always use a free
Yeah.
body diagram.
What are all the ones where there's like an X on the dot?
The arrow pointing to the dot.
Oh, they're pointing to the dot.
Yeah.
You got it.
Okay. We good?
It just looks like an X.
Okay. How about this?
Oh, these ones.
Okay, let's talk about these. So, okay, so we've got instruments attached to a weather balloon. Gives us the mass of the instruments. Gives us the buoyant force of the balloon that's pushing it upwards. Okay, now they give us a bunch of actually extraneous information on this, don't they? Because after the balloon is accelerated for 10.1 seconds, the instruments are released. A net force with a magnitude of what acts on the instruments after they are dropped from the balloon? So all that first part is completely irrelevant. Once they're dropped from the balloon, what's the only force acting on the instruments? Gravity, yeah. And so they're asking for a force here. Now, where people miss this, there's still some confusion about, what units do we use? What's a force? Really, if these are forces, what do the units have to be? Newtons, right. So if it's asking for a net force, I have to calculate the weight, which in this case is equal to m times g. What people routinely did on this is they put in 5.95. That's the mass, right? But that's not the weight. That's not the force. I'd have to multiply 5.95 times 9.8 and get, let's see, and get, okay, so what do I round that to? Hey, listen, this isn't gonna work. I want to go through this, and I want to get through it. We don't have a lot of time. I need it to be a little more organized here, please. So how many places do I round that to? 3. So 5.83 watts.
5.8
Newtons, good.
58.3.
58.3, there you go. 58.3 newtons. There it is. Okay.
Whenever it says the correct answer is, I always feel like I got it wrong.
Yeah. Okay, so these are also the ones that were supposed to be the easiest, and they ended up being the hardest. So let's talk about these, because they should be easy. Car moving down a straight road changes speed. Which answers include only action-reaction pairs acting in this situation? So let's talk about action-reaction pairs. What does it mean? What are action-reaction pairs? This is Newton's third law.
There's an equal
okay, so for every action force, there's an equal and opposite reaction force. I think the best definition is that forces always occur in action-reaction pairs. So how do we know, and we haven't, it's been a while since we talked about this stuff. So let's take a second here and just discuss this. How do we know when forces are in an action-reaction relationship as opposed to just forces acting on an object?
It goes over it in the opposite direction, kind of like, so let's say, the normal force is exerted on the car by the road, and then the normal force is exerted on the road by the car. Like it just
Okay,
goes-
right, so it repeats itself like that. The other thing is, how many objects are being acted on in an action-reaction pair? Two.
Oh,
Because an action-reaction pair, that describes the force that acts, it's a single force acting between two objects, right? So for example, the pen and the earth, right? There's a gravitational force, the mass of the earth pulls on the pen. Call that the action force. Then the reaction force is the mass of the pen pulls on the earth, right? They share that same force, right? The mistake that people oftentimes make with this is they'll think of things like, let's say we've got my hand pushing on the pen, providing a normal force that pushes on the pen, and gravity pulls on the pen downward. Those are not an action-reaction pair, right? How many objects were they acting on? One. Can't be, right? Can't be. The action-reaction pair has to be two objects acting on each other every time, right? So if we go back to this problem then, let's just cross these off one at a time, or pick the ones that work. The normal force exerted on the car by the road and the normal force exerted on the road by the car.
Yes.
Okay, that works. And we can just use our recipe, right? We know that we said that for forces to be action-reaction pairs, we have A acting on B and B acting on A, and they're opposite in magnitude and equal in magnitude, opposite in direction, right? So this works, doesn't it? So we got car on road, road on car, right? Okay, so that's a winner. Let's keep going. The frictional force exerted on the car by the road and the frictional force exerted on the road by the car.
Yes.
That's a winner, right? Okay, and it's the same, and it wouldn't work if we said what if we said the normal force exerted on the car by the road and the gravitational force exerted on the, right? I mean, then automatically we know it's off, right? It's got to be the same force acting between two objects. Okay, moving on. Oops, what did I do? Oh, I did something goofy here. Yeah, where does it go though? It went somewhere.
It went down to the toolbar.
It did? Are you sure?
Nope, other one.
No, Chrome.
It's right next to the one you clicked.
To the right.
It's right under the calculator.
Under the calculator? Where did you look at?
Left.
Right there. Was it Chrome? Oh, I know what it was. Yeah, okay, it was the test inside. Yeah, you're right. You're right. Gotcha. Okay. So, the normal force exerted on the car by the road and the gravitational force, right? It's not going to work. It's a normal force and a gravitational force. It's not the same force.
So what if we chose one?
What's that?
Yeah. So you get half or?
It depends. It depends how many you get. It's complicated, but you'll give you partial credit based on how many you get right and how many you get wrong and how many you get right. But I mean, like if you got just a couple of them right, didn't get any wrong ones, that would be pretty good. But if for every wrong one you get, it's going to subtract some points, right? Okay, so the gravitational force exerted on the car by the Earth's mass and the gravitational force exerted on the Earth by the car's mass. Yeah, that works, right? That fits. Everybody agree? Gravitational force exerted on the car, the Earth's mass, and normal force, not going to work, right? Two different forces. Gravitational force, normal force, nope. Frictional force exerted on the car by the road. That's just a single force, right? That's not an action-reaction pair, so that's it. Okay.
I overthought though. I was like, no.
Okay, what about this? Let's look at this. Person stands on a scale in a stationary elevator. The scale reads 748 newtons. Okay, so if it's a stationary elevator,
That's the normal.
right, the normal force and the weight are going to be balanced. Agree? So we now know that this is also equal to the weight, right? The weight is also 748 newtons. What would the scale read when the elevator is moving upward at a speed increasing at a rate of 2 meters per second squared? So the invisible hand would be pushing upwards, right? Okay, so if we drew the free body diagram then, we've got normal force pushing up, and that's what we're trying to solve for, right? The scale is actually measuring normal force. How hard is the scale pushing on us, right? So we got normal force up, and downward we've got the weight. I'll go ahead and just even put in the magnitude. We know it's 748, right? And so what's our equation of motion from this? What's the net force going to be?
mg minus 748.
It's going to be
Fn minus.
normal force, right? That's the positive force, minus mg, and we already know what that is. It's just 748, right? Equals, what's net force always equal? Ma. Okay, we know everything here. We have to calculate m, don't we? Right, how are we going to calculate m?
That divided by gravity.
Yeah, okay, good. We have this equation up here. We know that the weight is equal to 748, so m is just going to equal 748 divided by g, so divided by 9.8, right? So we can just plug all that stuff in. All right, so let's do the calculation here. What do we get? Oh, we've got to add mg to both sides then, right? Last step. Last step. Right? Okay. So then we get mg, we said was 748, plus m is, I'll put it in parentheses, m is just 748 divided by 9.8. Everybody agree that's just m? Times a, which is 2.0. So our answer is that. We get to keep how many sig figs? 3. So 901, right? 901 newtons. Okay. Okay, how about this one? A rope lowers a bucket at increasing speed. So in what direction is the acceleration acting? Down. So in what direction is the net force acting? Down. So that means which arrow, the up or the down arrow, should be bigger?
The down.
Oh, you're right. Hang on. No, the up arrow.
Yes.
No. You're right. Down arrow. Sorry, down arrow. Because the down arrow, because it's a net force down, right? So that's got to be the bigger arrow. So stop me when we get there.
Right, the second one.
Everybody agree?
Yeah.
Okay. 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 Well, this is kind of a trick question a little bit. These are sort of random. Same deal. You got this weather balloon, drops the instruments, blah, blah, blah. After the... Oh, no, never mind. This is different. Okay, so
Yeah, this is a
different one.
It's
Okay.
like acceleration.
Yeah. So free body diagram. What's it look like?
Mass.
Down, mg, upwards.
We've already kind of drawn one just like this, right? So upwards, we've got the force of the balloon, the buoyant force. We'll just call it F sub B. The B could be for balloon or buoyant, you choose. Downward, we've got mg, right? So what's the equation of motion here? What's the net force? FB minus mg equals what? MA, right?
Yeah.
Okay, because it's net force. What are we solving for?
Acceleration.
Acceleration. So all we're going to do is just divide by mass, right? Okay, everybody agree? And that's just stuff we know. Buoyant force is 875, M is 5.01, G is 9.8. Okay, so. So we'll put in parentheses everything on top. We get 87.5 minus 5.01 times 9.8, all divided by 5.01. Gives us rounded to 3 places. So what is that? 7.67 watts.
Meters per second squared.
Okay, good. We're dealing with acceleration. So 7.67 meters per second squared. Okay? Okay, how about this one? Okay, so you lift a book with your hand, accelerating it upward. What are the forces acting on the book? Select all that apply. So what are going to be the forces acting on the book? These are just going to be single forces, right? Okay. So the force exerted on the book by your hand and the gravitational force exerted on the earth by the mass of the book.
Yes.
Okay.
Do you know where the comments are?
I think Mr. Morioka might have them. I'm thinking, not sure. Okay, we all with me here? Yes or no on that first one?
No.
How come?
Because it doesn't make sense.
Doesn't make sense. Yeah. We're trying to find the forces acting on the book, and we've got a force here that's acting on the earth, right? That's no good. The gravitational force exerted on the book by the earth's mass, so that's on the book, and the force exerted on the book by your hand.
Yeah.
That's good, right? The force exerted on the book by your hand and the force exerted on your hand, whoops, no good, right? That's an action-reaction pair, but only part of that is acting on the book, right? Next one, gravitational force exerted on the book, so far so good, and the gravitational force exerted on the earth. Nope. Another action-reaction pair, but only one of those forces is acting on the book, so that one's no good. And finally, gravitational force exerted on the book, good. Force exerted on your hand, bad. So it's just that one. Okay. Okay, how about this? Really? So this is just a pendulum equation, right? Yeah. So we got, what is it, right here, okay? So we start with period equals 2 pi times the square root of L over G, right? Right. Okay? And what do we know here? We know the length of the pendulum, and we're just trying to find, no, we know the period. We're just trying to find length, right? Yeah. So what do we do?
So we divide 2 pi to the side.
Yeah, first we got to solve for that, don't we? Right? This formula doesn't work for us. This is formula for period if we're inputting L. We want the formula for L if we're inputting T. So we divide each side by 2 pi, sorry. Right? First. Oh, square both sides?
Yeah.
Okay. Last step. Right? So that's what we get. Plug it in. See what we get. So this gives us 9.8 times the quantity. 14.3 divided by the quantity 2 pi. Now notice the sign. Do the quantities make sense? Everybody see that? Oh, you can't see it. What? Now you can. Does that make sense?
Yeah.
Okay, squared. No, yeah, there we go, squared. So the answer is 50.8 meters. Okay. What about this guy?
Oh, it's a crate problem.
Great problem. Yeah, you're gonna get some different ones, but you're gonna get one like this, similar to this.
We should all write the same exact problem.
Okay, so get out your notebooks. I want you to take a second and set up the free body diagram for this one.
Johnny, you're rich.
No, I'm not, bro.
Pablo Picasso. No, what's that? What's that guy that made the
I know, there
Yeah.
the only thing that's extra.
Okay, here we go.
Is when I'm
Let's see.
really excited.
Let's have Austin. Tell me what's a force.
Which is
I'm
nice 'cause
gonna
it's
draw the
just
free
like-
body diagram. Give me a force, Dad. Okay, what direction?
Down.
Down. Okay, so we got Maverick. Give me another force.
That's my pants.
Normal force. In what direction? So we got all we've got here is we've got a crate that's resting on a surface, right? And it's being dragged across a flat floor. So in what direction is the floor exerting a normal force on the crate? Yeah. Oh, good. See lots of this. All right. Okay, let's see. Johnny, give me another force.
Friction.
Okay. So let's say we're the force the crate is being pushed to the right. In what direction is friction going to act?
Oh, pushed.
Or pulled or whatever.
To the left.
To the left. It's going to oppose the direction of motion, isn't it? So we've got a kinetic frictional force acting in that direction. And so what's the last force going to be, Sam? What's the
Push.
The push, okay, a push or the pull, whatever we're doing, and that's in this direction, right? So we'll call it F sub P for the push, I guess, I don't know, whatever, doesn't matter. So there's our free body diagram, right? So let's do equations of motion then. Okay, so let's have, Braden, let's have one equation of motion here, please.
Fn minus mg equals 0.
Good, okay, so we'll look at the vertical forces, right? The net vertical force is gonna be the sum of all the vertical forces. There's only two of them. So we get normal force minus mg equals what?
0.
How come? You're right.
Because they cancel out, 'cause it's 6 and 4 is
Okay.
not going up or down.
Good, there's no net force up or down because there's no vertical acceleration, right? So there's one equation of motion. Okay, another equation of motion, yes, sir.
F sub P minus F sub K.
Okay, good. So the push or pull force minus the frictional force also equals 0. How come? What's the key word up here that tells us? Constant velocity, right? So A is 0, right? So that also must equal 0. And we're just trying to find the coefficient of friction, all right? That's fine. So that comes in from the friction part, right?
Yes.
So we end up with F sub P minus, what's our model for kinetic friction? Times normal force. And if that equals 0, I could just add that to the other side, right? Come up with that. We agree?
Yep.
Okay, and then the last thing I need to do, I know the push force, I know the mass, I'm trying to find this, right? I don't know the normal force directly. Where can I go to find the normal force? First equation, good. So up here, if we add mg to the other side, normal force equals mg, so I can make that substitution, and then we're in business, right? Let's flip this around, so I get mu sub k times mg equals F sub p, if I flip it around to get the mu on the left side. Last step to figure out what mu is. Subtract.
So you divide.
Divide, there we go. Okay, and that gives us our mu. Okay, now look at this result though. Instead of just accepting this and plugging and chugging, think about this for a second, because this gives you a little insight into friction. What is the coefficient really doing? Well, it's saying how much frictional force did we get? Because the frictional force was equal to the pushing force, right? How much frictional force was provided relative to the weight, right? You get that? So once again, the lower the coefficient, the smaller this ratio is going to be. The less pushing force is required for a given weight if it's slippery.
Would it be a good idea to turn that into a percentage almost, like
Well,
6%?
you kind of could in this specific situation, yeah. So let's get an answer and then we'll talk about that. So if we plug in our values, we're just going to get 31.8 newtons divided by 4.74 times G. I don't really need the units there. And if we do that, we get an answer. Just to kind of test the reasonableness, what would you expect for the answer to be?
It should be small, really, really small.
Okay, but it's going to be kind of in what range of values?
Less than 1.
Less than 1, greater than 0, right? All right, so if we plug those in, we get 31.8 divided by the quantity 4.74 times 9.8. Gives us, that seems reasonable. To 3 places, 0.685. Okay, so you could think of that then, you're right, in this particular situation, because it's moving at constant speed and the push is horizontal, right? This is really telling us that the frictional coefficient means that you're going to need about roughly 68% as much pushing force as the weight of the object. So you could think of it that way. You really could. It gets a little bit hard to stretch that model like later in the next chapter when we're pulling up at an angle. And so then it tweaks things a little bit, because then you're going to be adding, can you just kind of visualize what that's going to do? So what if this vector were gone? What if this vector were gone and we replaced it with one like,
Oh, is that like the car sliding?
Yeah, I really want to go to the car slide.
the car sliding one? Okay, we'll go to that one. So what if the vector was like that? What if we were pulling with a rope and this was like our tension, let's say? Then you see that when I break that tension into components, just kind of looking ahead a little bit, there's going to be a horizontal component of the tension that's going to move the object to the side, but there's also going to be a vertical component of the tension up there, right? And if there's a vertical component of the tension, what's that going to do to the normal force?
It's gonna make it increase.
It's going to make the normal force decrease, because this is just going to offset the weight, isn't it? You see what I'm saying? So that's going to cause the normal force to go down a little bit, which makes sense. The ground's not going to have to push as hard on the object if we're pulling up on it slightly, right? Because part of the work of offsetting weight is being done by the tension in the rope. And so then things get a little bit weirder, right? Then it's harder to interpret what that means. Okay, yeah, as a percentage, it wouldn't make quite as much sense that way. But it's an interesting thought. So what do we get? 0.685? What are the units going to be?
No.
Nothing. It's a coefficient. It's unitless. Okay. Ooh, look at this. Okay, so this is a Newton's third law thing, right? So we've got this baseball traveling horizontally. Let's see, it's caught during the catch. The baseball speed goes from 30 to 0 in some amount of time. What's the acceleration? The magnitude. How are we going to find it? Kinematics. That's just kinematics, right? So we know the initial velocity is what?
30.
Final velocity?
0.
Time? And so then we wanna find A, which one do we use?
That one, number two.
Number 2, right? So if we're trying to solve for A, that's just gonna be V minus V naught over T, right?
Yeah.
So we can just maybe do that real quick. So V minus V naught over T. We just plug that right into our calculator to save time here, how about? Open up a set of brackets, so we're gonna get 0 minus 30, so we get negative 30 divided by, T, right? So 0.00499 is that. Okay, so that's large. Rounded to, boy, that's really big.
Yeah, it's all stopping like right now.
Yeah, yeah, it really is. Okay, that's a very large acceleration. Okay, that might be a little too large, but we'll see. So if we round that to 3 places, we just get 610 or 6,010.
You think that's too big?
So
That's pretty big.
I mean,
It's pretty big. Maybe if it was being hit by a bat, I could see it, but yeah, that's pretty big. Okay, so then what's the force acting on the baseball?
The speed, the gravitation.
Okay, we got too many things going on. What's it gonna be? Caleb, how am I gonna get it?
You times it by the mass.
By the mass. Okay, so we're gonna take that quantity, which I've got on my calculator still, times m, times, go away, 0.143 is that. Now the sign might not be right. Oh, it just wants magnitude, so it's gonna be positive, right? So positive 860, okay? And that's new, I guess that's pretty reasonable.
How'd you know to multiply by the mass?
By the mass, because the net force is gonna equal ma, right?
Mass.
Okay? And that's acting in which direction?
Away from the
Away
Away from the player. Yeah. The player's pushing on the ball there, right? A force with a magnitude of what acts on the player? Okay, and that acts towards the player.
Alright, I hope this car one does.
Okay? Last one.
See, it's not messing up on this one.
What did yours do?
So on mine, like even on the practice test, mine compares to like Peyton's. So the speed would be say 135 with no decimal.
Okay, yep, that is messed up.
So
Okay, it is. All right, I think I fixed these. See, this is my fault. I didn't go through and repair and like redo these before this section, a couple of these. So I'll fix that one. I'll fix that one. Yeah. Yeah. Do we have time for this? How much time? do we have? 1 minute? All right.
Come on, Mr. Wood. That one takes